Okay, so we are now recording. So let me hand the floor over to the last light benders who will describe their heliostat. I'm even embarrassed to say it. I hate Deborah.
Hi, good afternoon. We are the last light vendors. We are group 227B, and our heliostats name is Deborah, but our presentation title is I Hate Deborah. Um, Her name is short for or long for Deb, because we are 227B, and at one point she had um, red and white and black and yellow, and so it reminded us of um, Germany, which is DE. And our group members are Samantha Allen, Sheila Dunn, Andrew Janey, Trevor Perez, Jimmy Riggins, Andrew Robinson, and James Sanchez. Also, our title is because we had a lot of insane issues that were very unforeseen, and she was very moody. So an outline of our presentation is we're going to start with the head talk concept, and then go to key product specifications of our heliostat, then to prototype testing, specific features to our heliostat, calculations that led to our prototype, the evolution of our design, the CAD model, and some exploited CAD views, cost summary, value proposition, and a conclusion. So our hedgehog concept starts with our passion of 3D printing, and we use this for bespoke materials. Our skills as a group came from varying backgrounds from each of our members, including coding, 3D modeling, 3D printing, and mechanical and aerospace majors. So that allowed us to also quickly iterate parts um, in our prototype. To be economic, we focused on gears to increase torque, and gear ratios were used for both azimuth and elevation angles. We also used super glue to provide extra support for our weak materials so that we could test quickly instead of printing in other parts, and we were able to save materials through this. So these are the specific products within our heliostat. The products that were given to every single group that was included in our design was the power supply, the Arduino board, the limit switches, two NEMA 17 stepper motors, and stepper motor drivers. Specific to our heliostat, we had a height of about 40 centimeters, a width of about 20 centimeters, and a length of about 25 centimeters. We had two separate gear ratios, one for the elevation angle and one for the azimuth angle. The elevation angle was 128 to 11 to allow for about 180 degrees of motion and better torque and acceleration. And our azimuth angle was able to move our shaft. To prevent our shaft from a movability from downward and horizontal forces, we had two ball bearings within underneath our shaft and around our shaft.
Throughout the semester, we underwent several tests to demonstrate progress towards the final goal, which was the laser reflection test. And on this slide, you can see two of the tests that led up to that. The first of which was the motor control test, which demonstrated being able to control the NEMA 17 stepper motors using the Arduino control. This included being able to demonstrate that we were able to generate step commands with varying number of steps, as well as the direction of motor rotation, and that we were able to use limit switches to, in effect, home the motors, but at this point, they were not within the model heliostat. The second, oh yeah, and then there's a video that demonstrates us being able to do that. The second test that we were conducting was the azimuth elevation test, which included some components of the motor control test, but added on the fact that the motors were now within the design, as well as the limit switches. And in that test, we were given certain information on how many steps or how many degrees to move the motor. And we would perform those operations as well as demonstrating a homing function, which you can see in the video. So the next test that we performed was the wind survivability test. This test corresponded to the customer requirement for surviving ambient conditions in the desert. And this was done by testing a heliostat aerodynamically similar to the heliostat of our final design. And we tested it under 4 different wind speed conditions, which corresponded to a large fan operating 4 and 5 meters per second winds, with the heliostat in a normal everyday operating condition, which is the mirror at a angle which produces the most forces on the heliostat. And then the test progressed to a testing with a leaf blower, which produced 50 and 60 meters per second wind speeds. And for this test, the heliostat was in a safety configuration, which for our heliostat corresponded to a horizontal orientation of the mirror. And the final test, which was the ultimate goal of the course, was the laser reflection targeting test. And in this test, there were several goals that demonstrated our ability to control the mirror to redirect a laser. The highlight of which was we were given coordinates of the target, and we used our inverse kinematic solver to generate angles to input into our Arduino IDE environment to redirect the laser at the target. So we were able to demonstrate that we could hit the targets within the half a degree accuracy that was demonstrated by the, or required by the customer.
All right, I'll be talking about our guiding design philosophies. This is what we started out with in the beginning when we were altering. So as Sheila touched on a little bit, we were trying to utilize mainly 3D printed components, and that was so we could iteratively alter the design pretty quick and make use of the 3D printers that were widely available in lab. We also designed to minimize the number of fasteners. We were told early on to reduce the number of screws, so we tried to stick to it. We also tried to go with a low part count to keep the assembly simple. We avoided mechanisms which required adjustment, such as pulleys and tensioners. And we also prioritized internal placement of electronics, such as the motor and wiring and our control board, to reduce any environmental effects. Several of the key features of our heliostat are the large external elevation gear, as seen on the left. We adopted this to help with our precision on the elevation adjustments. Again, the fully 3D printed design. Most of the components were not off the shelf. We had them built in lab. We had a set of bearings, a thrust bearing at the bottom to support the weight of the heliostat main shaft, and then one radial bearing. You can't quite see in this. Past that, we were designing our gear ratios to maximize torque and reduce velocity. This helped us achieve a desired design goal for the accuracy of our elevation and azimuth gearboxes. As you can see on the left, we had our electronics fully enclosed. This again was to prevent any environmental interaction and to help with the aesthetic. On the right, you can see our fixed main shaft up at the top. A lot of it is hidden in between the two base pieces. All in all, I think we only had around 7 parts, which we did pretty well with keeping the assembly simple.
So along the way, we had 3 main calculations that we did to support our idea and prove that it would work in theory before we moved to an actual model. The first one was the gear ratios. The big one that we've iterated a couple times was the accuracy in the customer specifications. It required 0.5 degrees of accuracy at the target, which sounds reasonable, but for example, when we were testing at about 4 meters out, that's a circle with a diameter of about 2 inches. So to do that with the motors we were provided, we had to look at what we had. We had stepper motors, meaning they had a finite degree step with each click as their smallest movement of 1.8 degrees. To get that down to that 0.5 degrees of accuracy, we had to divide that by 3.6, meaning a 3.6 to 1 minimum gear ratio. We ended up with a 4 gear ratio as our azimuth to get just a little bit above that accuracy and still allow it to fit inside of our shaft since everything was contained in there. The second big calculation was the wind load calculation. We wanted to make sure that the upper assembly was not going to fly off or completely spin the motor in whatever way it wanted to go when it was subjected to the winds. To do that, we looked at the worst case scenario. Winds acting normal to the entire mirror surface, and it's acting at 50 meters per second, which is around 112 miles an hour. Using the area, the density of air, the velocity, we were able to calculate that produces about 54 newtons of torque, or 54 newtons of force, I'm sorry. And then looking at our motors holding torque and how the gears were set up in their configuration, we concluded that you only actually need a 1.4 to 1 gear ratio to withstand that wind. That's primarily due to the 2.1 or 2 centimeter acting force between the gear interaction. But on top of that, which is well overkill, our final gear ratio was 128/11. This was mainly to aid in the accuracy concerns, as previously mentioned. And the actual number of teeth was chosen rather arbitrarily, besides making sure that we're above that minimum ratio. The only other calculations that were of significant performance concerns were the inverse kinematics. And that, with our relatively simple model, a relatively simple control scheme, was just trigonometry.
So the design has been through many changes from when it was first sketched on paper to the final result used during the laser test. With the original advice from our teaching assistant, the shaft would be inserted into the base using the print and place method. With the print and place method, 2 separate parts that are made to be assembled are 3D printed, already assembled, so they cannot be taken apart and are still free to move. Before committing to this method of assembly, we tested print and place on a much smaller scale and noticed that the shaft would get caught on the base and we could not access the housing to add bearings or would have to reprint both parts if we wanted to change only one. Because of these factors, we decided to split the base into 2 halves and not do print and place. The next major design evolution was the iteration of the gearbox. The gearbox was sourced from Thingiverse, and once it was assembled, the shaft was able to rotate easily. Once the laser test practice stations were set up and we began testing our accuracy, both the azimuth and elevation gears were providing an inconsistent error. After testing every possibility we could think of, it was concluded that the error was caused by gear backlash. With backlash, there is a lag from when the gear starts moving to when it contacts the next and produces movement, causing the calculated laser distance to be off. The backlash was able to be significantly reduced by increasing the profile of each tooth to increase friction and remove the space in between gear teeth. The last significant design changes made were to the supports for the mirror backplate and backplate mount. The backplate mount would often break at the 2 pillar bases when printed at 20% infill or below. To combat this weakness, extra support was added around the pillars to reduce to reduce the bending force on the plastic. The backplate mount was also printed at a higher infill than the rest of the heliostat to ensure it would not snap under the wind force or any other external torque. The top backplate for the mirror also had similar supports added around the connection point to the mount to help in protection against the wind force. Here are images of our heliostat with exploded views showing the azimuth gear and set screw, top backplate mount and limit switch and its cover, and the motor and gearbox assembly. To reduce backlash, all of our gears have set screws to make sure parts rotate together without lag. The limit switches have covers placed on during assembly to protect the wiring from any outside elements and reduce wind from going into the heliostat and building up pressure, which would ultimately lead to failure. The gearbox was chosen for its small volume and low amount of parts needed for assembly. Following the desire to keep a low part count, the mirror, backplate, and elevation gear are printed as one part and attached directly to the shaft mount. The motor is placed directly in the shaft, which has a built-in shelf to reduce torque on the mounting hardware and the chance of failure. Heat set inserts are used to attach parts like the backplate mount to the shaft because they provide a good connection for screws and are easy to use for rapid prototyping. As discussed earlier, the base was split into two halves since it was decided that print in place was not the best option for rapid prototyping.
One of the key ideas behind our heliostat is design for manufacturability and low production cost, where most of our prototype consisted of 3D printed parts. The provided parts, or parts directly off the shelf, costed a total of $141.47 and were not included in the purchase cost. This purchase cost accounted for hose clamps, bearings, wires, fasteners, and 3D printed material. Our heliostat had 8 different 3D printed components. The components equated to a mass of 928.91 grams of filament material, where one unit of 3D printed material weighed 1,000 grams and costed $29.99. Prorating this cost for our needed material, the cost of 3D printed material came to $27.86 for our design. There is no manufacturing labor cost, but there is, of course, an electricity cost. The electricity cost accounts for running the 3D printer at 12 cents per kilowatt. Our energy consumption in total comes to $1.28 per unit. This cost includes a 5% increase, which accounts for machine upkeep over time. Factoring in these costs, the total to produce one unit comes to $94.04. This falls under the sub $100 customer requirement. Accounting for injection molding and labor required for mass production, it will then cost us $282,120 to produce 3,000 heliostat units.
We believe that our heliostat can provide customers with a robust, self-contained design at an affordable price. As we've discussed, we achieved this using design for manufacturability, which was achieved through many iterations to arrive at our final design, as well as low-cost 3D printed materials that allowed us to make those iterations, as well as make unique bespoke designs to meet our exact needs. Furthermore, all of our electrical components are contained within the base to improve the longevity of the system and prevent external failures. As we've discussed, we believe it meets the customer requirements necessary and that we've proven that through testing such as the motor control test, laser tracking test, and wind survivability tests. We thank you guys all very much for coming, and we'll now take any questions.
All right. Great. Thanks for the presentation. I did, by the way, just check in with the next group, and they're good to postpone for another 10 minutes or so we can proceed with a full 10-minute long question period without messing up the next group. So if there are questions from the panel, now is the time.
Yeah, Dr. Traum, I'll start. This is Rick Miles from Northrop Grumman. You talked about your base breaking consistently, and so you had to reinforce. I'm just curious if you did any sort of analysis prior to having the failures that would have indicated that that's where you were going to experience failures in your design.
Yeah, I'm glad to answer that. We did not conduct an analysis because we didn't really think about it truthfully. This was pretty much all of our first experience using 3D printing on a mass scale. And I think if we had made that design through injection molding, even, it probably wouldn't have had an issue. But I think with just the way that 3D printing layers on, it created that stress concentration just perfectly enough. And I think it just delaminated more than it being actually, I take that back. I don't think it was much a stress concentration issue as more a delamination issue of just how 3D printed material layers on.
Yeah, so if I'm looking at the picture that you're showing there, right, to the lower right, where it looks like you've added a triangular portion of material, right?
Yeah.
That's what you added in?
Yes, sir, and
So
the middle as well.
Yeah, so I think one of the issues starting off, right, is you did have a stress concentration there because you don't have a good radius transition between the base to the vertical, right? So you'd have to have a pretty nice radius transition, I think, there in order to not have failure. I really enjoyed hearing your story about the gear backlash. I think that's a good lesson to learn. Definitely something to that people don't really understand until they actually experience it in a design concept. And then the last thing I wanted to do is if you could go to your cost. So you had zero manufacturing labor, right? And I understand you were 3D printing a lot, but there was mention that, you know, when you move to mass producing, you're going to do injection molding or whatever. There's going to be some sort of manufacturing labor involved. You know, not everything comes for free and putting the stuff together. The other thing is, so going to the 3,000 units, it looks like we're just multiplying the 9404 by 3,000 to get that final cost. You should expect some sort of improvement in cost due to mass production improvements, and there should be some ways to you know, go calculate that. I know in the literature there's different factors you can apply to estimate what your mass production would cost would be if you're producing a lot of these. So just a couple of things I think you should go do some further investigation on.
Yes, I forgot to mention that. I actually noted it down to bring that up. That was just based on the one unit. But if we do mass produce, say things like even our fasteners, which come up to 300 units, like in a package, and we obviously did not need that many for our design. So you could also even decrease the cost just prorating factors like that as well. But yes, in our final report, we plan to take that into more detail and consideration.
Okay, great.
Can I ask a question?
Of course.
Sure. So on the cost to produce 3,000 units there, it does ignore the $141 in base cost. So that may be a little bit misleading. I'm sure you noted that, and there's a little asterisk there. The gear train came off of Thingiverse or something, I think I heard correctly. And it looks like it's some kind of planetary gear set. Obviously, it has the benefit of sort of having a coaxial drive, so you can line up the motor with the shaft. But there's lots of different ways you could do this. And the fact that you encountered a lot of backlash, were there other alternative gear configurations that you considered, and kind of, you know, maybe walk me through why this ended up being the best solution?
Yeah, I can answer that. So we chose the gear because our design was to have the motor inside the shaft to kind of reduce space and keep our overall design small. So we needed the gear to be in line with the motor, and all the other options we were looking at to achieve the same amount of gear reduction, we were looking at a motor offset, which would add more housing because our base has just enough room for all the electrical components. And at the time when we chose this gear, like once we assembled everything, it would spin the shaft, and we didn't have any testing yet for the laser. So we didn't actually realize that there was backlash going on. And so once we realized that that was happening, it was a little too late to kind of switch our whole design over to a different gearbox. So we just kind of had to make quick changes where we changed the gear teeth profiles to account for that.
Okay. What would be other possible? Did you look at other possibilities for coaxial drive trains?
Well, when we realized that this was not the best option, we still had to just kind of stick with it because of the time constraint. So we didn't look into others.
Actually, I think, didn't we try just directly driving it through the motor?
Right.
And
that was our, yeah.
Yeah, it did. It worked even worse because, you know, with the backlash we found is, even when we had the motors powered, as we rotated that central shaft by hand, we found, or as we tried to move the central shaft by hand, we found that it would rotate when it shouldn't. It was loose there. And I that was kind of our guiding area to reduce. And when we just tried to directly drive it through the motor, it was equally as loose.
Okay. Yeah, I just in kind of surveying other solutions, I saw, I think, a number of groups using harmonic drives, which are notable for, you know, typically having very low, if any, backlash, you know, high friction. I will say that globally, there's about an 18-month waiting time on trying to get any kind of harmonic drive, so I'm not suggesting it. But yeah, there's other configurations, so I was curious about that.
Right. If we had to do it over again, we probably would go with a different type of gear, like the harmonic drive, to just get rid of the backlash. So that would definitely be an option for the future.
Yeah. It is. I've heard. I'm not that experienced using stepper motors, but I'm aware that there's something called micro stepping, where you can get sort of sub-step displacements. And I don't know if that is motor specific, or was that something that you potentially could do just electronically to increase the resolution without, you know, having to do other things?
Yeah, we looked into the micro stepping once we started realizing that backlash was there, but it would still have, I know James can probably talk a little bit more about the micro stepping in the code, but I think, again, with the time constraint, we kind of just had to make the quick change of reprinting this with the larger profiles.
We did take a look at micro stepping, and there are a couple other groups, I believe, that wound up going with it. But one of the major drawbacks with microstepping is the loss of the torque of the motor. And we found that with the internal friction of our design, that by decreasing the torque of the motor would miss steps occasionally. And so that would produce another issue that would have to be addressed in another way. So we decided to stick with the single step option.
Okay. Great. I mean, I can't imagine why you say I hate Deb. I think it looks like you guys had a lot of fun. So
yes, we discovered these difficulties a week ago. So
thank you.
Okay, we might have time for just one more question if there's anyone else in the panel that wants to ask.
Can I ask one question?
Sure.
Okay, thank you. So I was wondering, in one slide, you don't have page number, so in one slide, you guys said the gear ratio, there's specific design gear ratio to withstand wind. I think I may need more clarification on that.
Yeah, so we really want to make sure that in the wind, so in the desert, in the wide open plains, you're going to see higher winds in general. Anywhere from 30 to 50 miles an hour are not uncommon. So we wanted to make sure when those winds came in that we don't shift off of our target.
So you have the wind force and the torque calculated, and then it directly jumped to the gear ratio. And as a structure person, I would prefer to something like, okay, for this force, for this torque, what is the maximum stress that can be generated if you consider the gear is the most critical part? And for the specific gear ratio, what is the stress that my gear can withstand? And then I can say, okay, for our design, I think this gear ratio is to withstand wind. But from a structure point of view, I don't see like any stress analysis.
That's really fair. One of my main concerns, or one of my main thoughts when I first think about that is that the anisotropic nature of 3D printing is going to make that analysis really, really tricky, and it's going to be very dependent on how the what type of direction the 3D printer prints the gear in. And frankly, I'm not sure I'm prepared to do that type of analysis.
Oh, okay. 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 Thank you.
Yes. Thank you for your question.
Great. Okay. Well, just for the sake of time, we probably should wrap it up there. So I want to thank the group for sharing your design with us, and especially the trials and tribulations that you guys went through on a short time span. When I write recommendation letters for students in MEC 2 and MEC 3, I describe the Capstone experience as being just like a beleaguered startup company, and you guys kind of embodied that almost perfectly, discovering that you had to deliver something today, and a week ago all of a sudden all these problems pop up, and nobody potentially slept for a week to get the problem solved. So it's a great experience for the real world, especially if you work for a small company. So appreciate you guys putting in the time and the effort, and blood, sweat, and tears to arrive at a solution, even though you encountered some pretty big barriers pretty close to the end. So it was noticed and appreciated, that you guys did that, and we're, I think, relatively successful. Like Dr. Banks said, I'm not sure why you called your talk "I Hate Deborah," given how successful the outcome seems to have been. But anyway, just wanted to state my appreciation as well for the hard work you guys put in this semester. So thanks for that.
Thank you, Dr. Trom, and
Thank you, Dr. Trom.
and Kathleen and
Thank
DG. Thank you two for all the help you've done this semester. So and everyone else, thank you very much for coming and the questions you had.
Yeah, thanks everyone.
Thank you for your feedback, everyone.
Good job.
Very good. Okay, let me stop recording.